Colleagues, ladies and gentlemen, welcome to the HKIAS Distinguished Lecture Series on Electronics and Photonics. Today, I'm very pleased to introduce to you Professor Ding-Ping Tsai, who will give us a lecture on meta devices from sensing and imaging to quantum optical chip. Professor Ding-Ping Tsai is currently Chair Professor of Department Electrical Engineering at CityU. He is elected Fellow of 12 professional societies. He is the author and co-author of over 330 SCI papers, 65 book chapters and conference papers, and 39 technical reports and articles. He has been granted 68 patents in the USA, Japan, Canada, Germany for 45 innovations. 20 of his patents have been licensed to 5 different companies. He has been an invited speaker for international conferences or symposiums for more than 300 times. He received more than 40 prestigious recognitions and awards, including Global Highly Cited Researcher from Web of Science Group, China's Top 10 Optical Breakthroughs in 2020 and 2018, Mosley Award from the International Society for Optics and Photonics. He was editor of the Journal of Progress in Quantum Electronics, associate editor of the Journal of Light Wave Technology. He currently serves as editor of Light, Advanced Manufacturing, and Photonics Insights. He is also a member of editorial board of several research journals, including APL Photonics, ACS Photonics, Advanced Optical Materials, Nano Letters, Physical Review Applied, Optics Communications, Small Methods, Advanced Quantum Technologies, Optoelectronic Advances, Postmonics, Optoelectronics Letters, and the Frontiers of Optoelectronics. Without further ado, let's welcome Professor Tsai.
Thank you, Professor Yan. Thank you very much. Let me share my screen. Good afternoon. Many thanks for the kind invitation and the arrangement of my talk at Hong Kong Institute for Advanced Study, HKIAS today. It is my honor and pleasure to present my talk, Meta Devices from Sensing and Imaging to Quantum Optical Chip. I will report the current progress of our research on the development of high-dimensional optic meta devices, especially the achromatic meta lens array and their applications in light field sensing, imaging, and quantum optics. Because the title of this talk is Meta Devices, quite a few people ask me about the relationship between the meta device and the metaverse. I will explain my comments and views on this question at the end of this talk. First, I would like to thank my former student and the current graduate students for their great efforts of the results shown and report in this talk. They all had a very good position after receiving the PhD degree, and they serve research scientists at Harvard University, EPFL in Lausanne, and also Weekend in Japan, and Caltech in California, and University of Southampton, and also TSMC. and also my current student in the CityU. And also our research collaborators around the world. There are many good friends from Nanjing University, Fudan University, and also National Singapore University, National Technological University in Singapore, Hokkaido University, Riken Japan, University of Southampton, Harbin Institute of Technology in Shenzhen, and the University of Science and Technology of China, Rice University, Caltech, University of Massachusetts, Boston, and the Academic Seneca, and the National Taiwan University. This is the outline of my talk. I will first give a brief introduction of metamaterials, meta surfaces, and some of our previous study on meta devices and their applications. I will show you the reasons for developing the meta lens and the achromatic meta lens. I will provide you the general design principle of meta lens. I will report how to use our novel method to make achromatic meta lens for reflection. Similarly, I will show you how to make our transmission type achromatic meta lens and meta lens array for light field sensing, imaging, and quantum optics. Finally, I will summarize my talk with the prospect of meta devices. What is metamaterial, meta surfaces, and meta devices? Material is made of molecule and atoms. In crystal, the atoms are arranged in a periodic fashion with lattice constant less than 1. This is much smaller than the wavelength of the light. Therefore, the light experiences an effective homogeneous material normally. For metamaterials, it's made of artificial atom and molecule. The artificial structure is on a sub-wavelength scale with a lattice constant around tenths of the working wavelength. By tuning the feature, size, and the geometry of the artificial structure of metamaterial, novel and extraordinary electromagnetic phenomenon can be found, which cannot be found in nature, such as negative reflection and the left-handed material. Professor Visarago calculated and predicted the left-handed material are negative refraction with negative permeability and permittivity in 1967. David Smith and John Pendry, they published the first microwave experimental results from 8 to 12 gigahertz experimental results of the left-handed material and the negative refraction phenomenon in 2001 and 2004. We made the toroidal metamaterial and report the first microwave toroidal response in 2010. Subsequently, we experimentally demonstrate the narrow structure toroidal metamaterial with the toroidal dipole and anapole in the optic wavelength regime. So a lot of people in the past few years keep asking me, when will the metamaterial commercial product be available in the store? I have also received letters from the Nobel Prize Physics Committee 2 times for soliciting me, for soliciting my comments and views on this practical application of metamaterial issue. When will the metamaterial or meta devices be commercially available in our daily life? It is a very good question and a great challenge as well. I hope you can find out the answers to this question in my talk today. One of the simple answer is to consider the meta surface, a single layer of meta material. In 2011, Dr. Yu Nanfang, in his science paper, he showed the meta material with narrow antenna used to demonstrate the wave front of the propagating wave can be fully controlled. 8 different narrow antenna can generate 8 different phases to form a new wave front. It means that arbitrary wave front can be generated by the design of artificial narrow antenna at the interface. Of course, the size of the period of the narrow antenna are small compared to the working wavelength here. In the textbook, Huygens Fresnel principle said that every point to which a luminous disturbance reach at the interface will become a source of a spherical wave here, and the sum of this secondary wave determines the form of the wave at any subsequent time. The Snell's law is based on this simple principle for a perfectly flat interface. That is, for the normal incident case, the generated wave will be in the same propagating direction as the incident wave. However, for the interface with meta structure, the extract momentum k vector is generated here, and the sum of the propagating k vector determines the propagation of the incident wave. This is called the generalized Snell's law. Okay. And in general, meta surface with narrow antenna can be used to generate different phase, polarization, amplitude, optic angular momentum, and so on. That means the incident electromagnetic wave can be manipulated by specific designed meta surface for various optic applications, such as the wavefront correction, imaging, structure, color, sensing, optic communication, and the display. Many applications here. However, to control the narrow antenna to generate different phase for the coverage of the entire 2-pi phase maturation. In the beginning, people used the narrow structure with the V shape, which oscillate in one direction and to the other direction in order to cover pi plus pi, so the 2-pi. But the disadvantage of this case is each of these narrow antenna had a different cross section. Therefore, they have a different interaction efficiency quite differently here. That means for different wavelengths, resonance had a different efficiency. So later on, people improve it, use the geometry effect. It's so-called the PP phase, Berry phase effect. Use the similar narrow antenna here. By rotating the angle theta, you will have 2 theta phase difference generated here. The advantage is the size and the shape are the same, so they have the equal amplitude of the efficiency. However, the total interaction cross-section for those 2 cases are quite low because the coverage of the narrow antenna compared to the total surface area is relatively small. So to improve this case, we report in 2012 using this mirror image of the narrow antenna. So for the narrow antenna made of the metal, we have the plasmonic resonance around the narrow antenna in one direction, and then generate the mirror image which oscillate in different direction. It's another electric dipole generated to cover two pi phase. Okay, one is 180 degree, the other one is negative 180 degree. In this way, we generate a magnetic dipole, and also the mirror image will increase the efficiency. But the disadvantage is it's confined for the reflection mode instead of transmission mode. Okay. So based on this, we study many different meta devices, including the application of this gradient narrow antenna meta surface for beam diffraction, and full color meta hologram, and the versatile polarization generation and analysis, and also the full color routing using the various novel meta surface. We also demonstrate the epsilon near zero tunable meta surface for beam diffraction application. In this talk, I mainly focus on the design, fabrication, and application of novel meta devices such as meta lens and the meta lens array. So I will talk about a little bit optic quantum chip in the end of this talk. Okay, so let's start. What is meta lens and achromatic meta lens? This is this is the outline of my talk. So I will first talk about the meta lens. In our daily life, optic lens can be seen everywhere. For example, camera, mobile phone, microscope, and so on. For full color image, wideband working wavelength is needed, and the chromatic aberration appeared due to the dispersion of the material in nature. To solve this problem, people normally have to design a complicated lens set to have aberration-free full-color wideband image. This also leads to very complex design and bulky system. However, meta lens use a narrow antenna of meta surface to manipulate the light. It is flat optics without spheric aberration. The narrow antenna acts as the secondary light source for the light emission, which can be polarization dependent. The polarization image can be easily achieved. The advantages are lightweight, compact size, novel function, flat optics, and the CMOS mass production process. In 2015, different narrow antenna were used to focus the various wavelengths. They show the combination of different narrow antenna had the same focusing position for few discrete wavelengths. Subsequently, for the achromatic focusing purpose, 3 meta surfaces were used for the focusing at the same position. The problem here is the focusing efficiency after going through 3 meta surface is quite low. In 2017, the combination of various narrow structure can achieve a chromatic meta lens with 60 nanometer bandwidth in transmission mode. So this is a very challenge issue there. In principle, to realize a chromatic meta lens or achromatic meta device in wide range of the frequency is possible. I will show you our general design principle of meta lens and the meta devices. If we consider the meta surface as a transformation tensor matrix, the output can be calculated with the known input and expected output. The solution of the wavefront transformation tensor matrix can be found mathematically. Okay, so with this function of the lens, we basically expect the focusing function. So we know the incident line is in parallel. So the plane wave in parallel incident beam and the focusing spot is known. So we can find out what should be this transformation tensor matrix for the meta lens or meta devices. In reality, the process for design meta devices, how to realize the solution of the transmission tensor matrix of these meta devices or meta lens can be very challenging. The purpose of the meta device may have multiple modulation requirements such as amplitude, phase, polarization, orbital angular momentum, high harmonic nonlinearity, and even quantum entanglement effect, and so on. In case you try to integrate or combine various neural structure to the integrated resonance unit to satisfy all the demanding specs shown here, optimization is needed at certain point in order to accomplish practical and useful meta devices with high efficiency and novel functions such as achromatic or chromatic polarization conversion or vortex beam generation, quantum entanglement, nonlinear signal generation, and so on. So I share with you our general design principle here. No matter what kind of the material used for the neural structure, with the known permittivity and the permeability, epsilon and mu, one can find out the wavelength-dependent reflection index and the extinction coefficient N and K here, which is wavelength-dependent. Okay. And by using the simulation software such as CST and the COMSOL multiphysics, the transmission and the reflection spectrum can be found for neural structure with known geometry and configuration. All the data collected can form a big data. Okay. And this big database for the information on the efficiency phase, polarization, and integrated resonance unit is very useful. Subsequently, with the known specification of your meta device, for example, your requirement of your meta device, then with limitation, within this limitation of application, that is the critical dimension and the empiric parameter of the production, then you can design the CMOS mask or photo mask or E-beam or for optic mask. Then you can have this layout come out and generate views for the large area, high precision, grayscale processing and engraving process or etching process and deposit process and coating process. Finally, you have your devices ready for the measurement and the test, and also for your application of this meta device. So this is the whole design principle for our meta devices. After sharing our design principle, I would like to share the first case of our continuous broadband achromatic meta lens in reflection mode by using the concept of integrated resonance unit, differential phase equation, and the edge alignment method. In the first case, we show you the focusing with no chromatic aberration over a continuous broadband wavelength from 1200 nanometer to 1680 nanometer in the infrared region. As you can see here, to implement the achromatic meta-lens focusing, then we use multiple resonance antenna to form the integrated resonance unit instead of single narrow antenna. And also we use PP phase, so-called the Berry phase effect, to successfully accomplish the continuous broadband wavelength focusing. And so here shows you the optic image of our lens made and the SEM picture of our lens. If you zoom in to this, each of these narrow antenna integrated resonance unit, you found is a gold mirror layer and dielectric layer with the thickness of 60 nanometer, and also the 30 nanometer narrow antenna made of the gold on the top. And normally it can be one or two or even three narrow antenna to be integrated as a resonance unit. Okay, and so for this particular case, we have the diameter of the lens is 55 micron. The focal length is 100 micron. Numeric aperture is 0.268. And the number of antenna feature size is 23 different types. And the total narrow antenna is 60,000. And the efficiency of this lens is about 31%. Okay. So this lens actually, if you check, there are 23 different features of the narrow antenna unit used in this broadband achromatic lens. For example, the narrow antenna unit A here, you can find out their size and their dimension here. They had this 10 narrow antenna with 60 nanometer width, 450 nanometer length, and 25 nanometer gap distance, which is used for 30-degree phase compensation purpose. For the, from the center to the edge of the lens, there are 50 different zones with the chosen narrow antenna unit type and the specific rotation angle for control of the PP phase. So this is the lookout table, and we actually make this kind of lens take advantage of this symmetry, circular symmetry of the lens. So, and also the design principle of our achromatic meta lens is shown here. We use traditional focusing lens, we use the traditional focusing equation for the optic phase, such as the function of meta lens radius shown here, and the wavelength for the working wavelength lambda. We use the differential phase equation. In this equation, one is for the basic phase control. The other term is for the phase compensation. We intentionally align the edge of the phase function curve of the maxima and the minima wavelengths, okay? And to have the large phase difference in the center of the meta lens. Normally in traditional optic lens, the curvature is flat in the center and bended a lot at the edge. But we do it differently in the meta lens. We make the most important structure in the center instead of at the edge because it's flat optics. Okay, so this is very important and very interesting. So we use the Berry phase plus the edge alignment method and the integrated resonance unit. We actually can design the principle, the primary phase control using the Berry phase by rotating the narrow antenna angle. We have two theta phase control to cover the 2 pi phase. And also we use the integrated resonance unit. We coupled different narrow antenna together to form an integrated resonance unit in order to make the resonance band broader and also high efficiency. So then we can have the compensation of the phase difference for this kind of different wavelengths. Okay. So in this way, we design our beta lens and generate this lookup table, which had a different integrated resonance unit of the different shape and different size and dimension shown here. Okay. And so this is the experimental result, and this is the simulation of our focusing effect for different wavelengths. Okay. For the wavelengths of 1200 to the wavelengths of 1680 nanometer. And we also generate, we made different different new numeric aperture lenses, and we find this is all achromatic because they are quite even at the focusing spot. And also compared to the this PB phase only meta lens, we had very good results compared to the only PB phase. It's a chromatic meta lens. We have very good results compared to that because it's flat here at the focusing spot, but it's not flat. It changes for different wavelengths. So, so for another case, our example I showed to you is to cover the visible spectrum. Previous one is for the infrared region. For the 400 nanometer to 670 nanometer wavelength region in the visible spectrum, we made this illuminant beta lens. Also, similarly, we have the integrated resonance unit looks like this, and also the diameter of the lens shown here. This is optic image is 41 micron. The focal length is about 163 micron. Numeric aperture is 0.124, and the total different narrow antenna feature size is 14 different types. Altogether, the total number of the antenna in one meta lens is 34,000. And the efficiency, the average efficiency is about 26%. Okay. And similarly, we have the different narrow antenna, different integrated resonance unit from the center to the edge. We took advantage of the circular symmetry to design this meta lens. And we take this similar design principle using the phase differential equation and the edge alignment method. We intentionally make this phase difference change in the center, and then we make this lens. This is SEM picture of our narrow antenna. This is the performance of our measurement and simulation, and it covers from 400 nanometer to 650 nanometer in the visible range. If you carefully check from the edge to edge, the narrow antenna in the center is more complicated than the edge. But actually, each of these narrow antenna, they rotate a different angle for different position. Okay, this is just a single strip took from one end to the other end, just to show you how it changes. Okay. Okay, with this in mind, similarly, I will show you how to make our transmission type of achromatic meta lens. Both two cases I show you are the reflection type of meta lens. Also, is achromatic because our novel method for design this kind of system. And here shows you the SEM picture of the gallium nitride achromatic meta lens. which is quite transmissive. With similar design principle I shared with you previously, we design and fabricate the transmission type achromatic magnetics using the gallium nitride. I will tell you why the gallium nitride later. Shown here is the SEM picture and also the zoom in at the different area, A, B, C, and the D, the H here. You can see the narrow antenna, which is actually different rotation angle for different narrow antenna. The height is 800 nanometer, and also the depth of the cavity is also 800 nanometer. So this type of beta lens is quite similar to the previous one. We had this different dimension for the different narrow antenna and also the cavity in order to cover the 2-pi phase change. And also we take the advantage of the circular symmetry to design this kind of beta lens. And here shows you the narrow rod and the narrow cavity for their resonance for different wavelengths. And they covered quite broad band coverage of the wavelengths. And also, I would like to mention to you why we use gallium nitride. Gallium nitride actually is a very precious material. However, the price is quite low because for semiconductor electronics company, they make this gallium nitride wafer for making the LED. So most of this satellite or the space program, all the semiconductor electronics, they need to be more stable and strong. So they choose the gallium nitride semiconductor electronics device instead of silicon. Because for the gamma ray and for the this commistic ray from the outer space, basically the lifetime is short in the silicon case. But for gallium nitride, it's quite high index of refraction, is very strong in physics property, and also the structure is very strong and stable. Most important thing is when we make the lens, people will ask the question, when the laser incident to your narrow antenna, will they be melted by the strong laser beam? Okay, so, but if you check the conventional optic lens, they basically, the peak power, they can be, the threshold of the peak power is about 9.3, 10 to the 11 watt per centimeter square. But for gallium nitride, it's 130 millijoule per centimeter square. And for the pulse of the femtosecond at the wavelength of 800. So it actually is 20 times stronger. The threshold is much higher. So when we make this kind of lens for focusing, it has to be very strong. Okay, so this is the reason we use the gallium nitride. And we use the standard semiconductor electronics mass production fabrication process. So we can mass production our meta lens or meta devices using this kind of system. So, and like I showed you previously, this is our results. And then we actually measured these results and we found excellent quality from 400 nanometer to 660 nanometer in the visible wavelengths. Actually, the focusing is excellent and also is achromatic. Okay, so this result is very important. The reason is we are the first group make this achromatic meta lens and showing the imaging of the full color image. Because most of the people, they make the meta lens and report is for single wavelengths. So for single wavelengths, it's easy to make because the narrow antenna you only resonance for one wavelength.
But for the broadband, for the full color image, you need to have a magnetic meta lens. And I don't spend too much time to talk about all this property for the different numeric aperture, but we have a very good efficiency and focusing effect. And also the resolution shown the standard resolution chart. Just use the white line source, like the lamp that we are able to use in our lens. This lens is only 15 micron in diameter. We are able to resolve the third part of the number 7. That's equivalent to 2.2 micron in this white light broadband non-coherent illumination cases. So that means the resolution is almost defective limited. So, and we actually also took the movie of this using this lens, and we found very interesting results, and we have very good cartoon movie shot using our lens. And my student have this. This is just the city on the city road and stop for the green sign, and you can see the outside the motorcycle and car moving. Okay, so this is very good and very important. So the meta lens is considered as the top 10 emerging technology in the World Economic Forum in 2019. And so people expect this thin and the flat meta lens could replace bulky glass for manipulating light. Okay, and however, I have different point of view. I will show you how to use our transmission type achromatic meta lens array for light field sensing, imaging, and quantum optics. Okay. The reason is I like small. Many people like to make a large diameter meta lens to replace the traditional optic glass lenses. However, for your cellular phone, this lens is very good, excellent lenses. They are very inexpensive, just $2 or $3 in total for the whole system. So I don't think we should replace this kind of lenses just because meta lens is new. Okay, I think we should think about the advantages for the small diameter of the meta lens. The reason is clear, as shown here. Okay, for the small lenses, you have large depths of the field. Okay, so if you think about for the imaging purpose, the advantage of the large depths of the field can be found in the nature from the nature creator. The God gives so much difference for the eyes of the ant and the fruit fly, and around the similar size as the meta lens. They all have large depths of the field for imaging. So there are around 80 lenses each side for the eyes of the ant. And ant is for two-dimensional motion. And for the fruit fly, they had about 800 lenses each side for the Drosophila, so-called the fruit flies. Okay, so basically the depth of the field is infinity for meta lens. So this is very important because for imaging purpose, a large depth of the field is very much in demand. Okay, so we learned from the nature creator, the Coensia is so-called the killer fly. There are around 2,300 lenses on each side of their eyes. And Coensia is 3 times faster and more sensitive than the fruit fly here because they got more lenses in their eyes. they have 8 to 9 times more imaging and sensing frame rate than human being. For the human being, normally we have about 24 to 30 frames per second. It's very difficult for us to catch the cohesia by bare hand. The reason is very simple. We only have 2 eyes. Okay, and so we learn from the nature creator that insect has the small and the compound eyes. The advantage are the large depths of the field and high sensitivity in optic image. For this reason, we design and fabricate 60 by 60 broadband achromatic meta lens array. The diameter is only 20 micron, and the focal length is 42 micron. So this is quite similar to the insect. Okay, here I show you this lenses array we designed. Okay, this is how it looks like. It's about 1.2 millimeter by 1.2 millimeter area, and we have 3,600 gallium nitride achromatic meta lens and made here. This is SEM picture, and zoom in, show the lens is excellent, and 20 micron in diameter of the lens. And this is the SEM picture showing, show you the height is 800 nanometer for the narrow rod, and also 800 nanometer depth for the narrow cavity. Okay, and with this type of lens, in total you have about 1.2 million. You have about you have about 9,350 narrow antenna in the whole lens array. In one lens array, in one meta lens. And in the whole lens array, you have about 3.4 million narrow antenna. So compared to the traditional compound lens for the live field imaging 30 or 40 years ago, the compound lenses using the molding glass. The disadvantage for this kind of lens is the defect issue, and also the spheric aberration, and also the whole array has quite unequal performance normally, so it distorts the image instead of collect the three-dimensional information. So not so much successful due to many problems of the lens array in traditional molding lens. But for our case, it's quite different. We are flat. We don't have spheric. We don't have this spheric aberration, and we can simply use this lens and put it in front of our collecting lens, and then we can have our image ready immediately. And this this is using a family camera. Put it after you remove the lens, and then put our meta lens array in front in your home camera. Then you take this image, and this image actually can show you the very large depths of the field. And here shows you the ABC at the different depths from the lens here, and then we can immediately find out by compare the image to the adjacent image. We can immediately find out the distance for the object. Is near object or far object. Immediately we can find out. So the disparity can be calculated, and we know the pixel size. Therefore, we know the depth immediately. So here shows you the depth image. This is a photo, and this is the depth image. Okay, and the disparity from our live field imaging can be calculated easily. And here shows you a model rocket from Earth to the planet, and we have this moving object on the optic table. We set up this and remove this rocket. We can have this movie, and shown and measure the distance for the moving object. So this is very important and very easily for this kind of meta-lens array. And also for the three-dimensional edge detection is very important for sensing purpose. So similarly, we find out the motion and the edge of this object. We are able to find out the edge immediately for the live field imaging. And so this is very easy for three different depths, and also we actually can have the edge defined and observed immediately. So for the standard resolution chart, we take the live field image of the standard resolution chart. Immediately we can have the rendering image showing this edge detection, and we also show the further improvement of the resolution to the group number 8, the first part. So that's equal to 1.95 micron line width resolution under this white light non-coherent illumination. So this is almost diffraction limit performance. So this kind of performance make this moving object to be imaging and sensing easily for the different purpose and also sensing purpose. So finally, I think my talk time is almost there. So I still have 8 minutes. I will share with you, briefly discuss our new development, optic quantum chip, and the prospect of meta devices. Okay. As we all know, we found that our 60 by 60 gallium nitride broadband achromatic meta-lens array with 33 million narrow antenna is small and accurate, high efficient, with large depth of the field, rigid and strong, low profile configuration, low energy consumption, and the CMOS process compatibility for mass production. So all these important advantages, let's make us think about the important future of this kind of beta devices. With the very strong demand of the multiple lens optic system shown on your cellular phone, the advantage of our meta-lens array are very obvious. This is the cover page of the IEEE spectrum, and it says the last and the best hope for the standalone pocket camera. Let's check this state of the art. Okay, they had many of these lenses, and it's very bulky and heavy. So the weight of this pocket camera is 3 times heavier than your iPhone. So you carry a stone in your pocket. Okay. So I think we want our meta-lens to have novel function instead of to compete with the traditional optics. This novel function, which is not available by the traditional optic lenses, and for the new application on the machine vision, AR, VR, and autonomous, and also robot sensing, future drone, and the video imaging or medical purpose inside your body. And so we think this should be the future. So to show you what we did recently in the CityU, we already made the first meta-lens drone in CityU. Okay, actually flying indoor, and you can see the picture, and we took the fish and picture of this whole thing. And by different height, we actually put a piece of the paper on the ground, and we can see the height. We can find out our aviation of this drone. And this is our lens. The lens size is quite big, and we actually can make and put together with a single sensor on this drone. So the advantages is lightweight, and also the consumption of the energy for the drone is very limited. And also people think the meta optics and metaverse, what's meta devices for the metaverse? This can be easily think about it, because you are not as rich as this guy, and you won't have all this huge display at home like him. Okay, so instead of wear this heavy and stupid goggle on your head, looks like insect. I believe in the future, people will have many wearable portable devices, or the eyeball engineering, which is near your eyeball, and it can be lighter, heavier, to display or to transmit for different reasons. So I think the meta devices is quite important in these cases. So I won't talk about too much about this because we are working on this, but I will show you the top 10 emerging technology for the 2020, including the AI, 5G, IoT, serverless computing, and biometrics, and AR, VR, and blockchain, robotics, and natural language processing, and quantum computing. So I think there are many possibilities for meta lens to be used for those top 10 emerging technology shown here. One of this example I want to show you is our work published in the Science recently for the quantum computing. The basic problem which hinders the high-dimensional optic quantum entanglement is the decay and the loss of the originality in the cascade of the quantum entangled light source. Okay, and you ask me why this optic quantum entanglement chip is important. Because you don't want to have this low temperature. You want to have the room temperature. You have to choose the optic chip instead of electronics chip in the this 270 degree C under negative 230 degree for those quantum effect happen. So the quantum effect happen for photonics is easy, but the problem is the decay and loss of the originality in the cascade process here, shown here. So it's very highly demanded and the challenge issue. So we made an optic high-dimensional quantum entangled chip, which consists of this very thin baryon borate BBO nonlinear crystal attached, integrate with our meta-lens array. And this meta-lens array actually focusing into this BBO crystal to have this down conversion of the photon generated, this down conversion photon pairs, which generate in pair, okay? And so this is the optic image of our sample. This is SEM picture of our sample. This is the optic image of the photon pair generated. And we randomly select two of them, or three of them, or four of them. We have excellent quantum entangled result. It's 98%, 96%, and 95%. That means we actually had this mutual quantum entanglement by each of these quantum pair, and also the mutual quantum entanglement of two pair, three pair, and four pair. So this is excellent result, and with important meaning. I actually show you for the conventional computer, you have 0 or 1, like this coin, okay? 0 and 1. But for quantum, the quantum qubit is not 0 and 1. It's multiple state. Can be 0 to n minus 1. So for the qubit, you have all the possibility which is entangled together, okay, correlated and entangled. However, if you consider the digital bit and the quantum bit, they actually entangled for many states. But for our work, they actually entangled to each other, not just self-entanglement, also mutual entanglement for 100 pair of the photon, down conversion photon. So all the possibility is much larger than this self-entanglement case. So I hope this will help you to understand, because too many slides for this talk, so I only choose 3 of them. But I will show you in the near future how they use for this quantum computing, communication, and quantum optic security. And this is our chip looks like. Okay, it's quite small, but we believe for the different purpose, we will have quantum communication and also quantum computing and quantum detecting and the sensor ready for this kind of optic quantum chip made from this meta-lens array system. So to summarize my talk on time, I would like to remind you what I talked. I first introduced meta-material, meta-surface, meta-devices, and also the general design principle of the meta-lens or meta-devices with novel new method using the differential phase equation, edge alignment method, integrated reference unit. And also I showed you the example for the reflection and transmission type of the achromatic meta-lens, and with broadband full color image in the display. And we demonstrate the multidimensional optic sensing and imaging, and also edge detection using our meta-lens array, and also our meta-lens array for high-dimensional quantum entanglement light source optic chip is shown. So I trust the small and the flat is the beauty and the great advantage for our system. Yeah. Okay. So this is the list of the paper I reported in this talk. So our paper shown here. I hope this talk will help you to understand our work, especially in the CityU. I joined the CityU just a few months. So I hope we can have our laboratory soon. And then you are very welcome to discuss with us. We are still learning the whole environment in the CityU. And we look forward to have close research collaboration with our colleague in CityU. And thank you. Thank you very much.
Thank you very much, Professor Tsai. And it's a very interesting talk. Any questions from our audience? Let me ask you a question first. You showed a page. You have like a matrix multiplied by another matrix. So you have matrix in, matrix out, and that's a transformation. I guess this is done in a analog way, right? So this is all done by waves and those. That's analog signal processing, right?
Yes, yes, you are right. You are right. This is just a classical way.
This must be very fast. But what about accuracy? So if we do this digitally using electronic devices, and what do you think about the accuracy?
Okay. I think you are right. Basically, if you make electronics like this SLM system, you actually can do a similar thing for this kind of devices. I trust it's possible. Just the limit is how much resolution and how much this pixel you have from your system to do it. So you are right. No problem. Yeah, this is just a concept. Okay.
Okay. Any questions from the audience? Maybe I ask you another question. You had all those, you use meta devices for imaging and etc. Then if I can say that the resolution of the images are still a bit low, is that right? What's the resolution you currently have? Resolution.
Oh,
yeah.
The resolution is good. It's as I show you, the resolution basically is diffraction limit. The problem is efficiency. The efficiency of the light collection, which is related to the interaction cross-section of the narrow antenna on the total surface area. So that's the efficiency. Okay. So for different system, you actually can, like I mentioned here, okay, you can optimize, depends on which one is more important for you. And then you can optimize your system for high efficiency or for different function you choose. So in this way, you can make your meta devices depends on your purpose. Yeah.
Thank you for such a. Any questions? Professor Chin Pan and let me see the video. Yeah, please. You can speak. You can unmute and you can speak.
Okay, Professor Tsai, thank you very much for very interesting talk. I'm not in your field, but for your last conclusion, you mentioned that small and flat is the beauty and the great advantage. But for natural eyes, I mean, for example, the compound eyes of insects, maybe I misunderstood, okay? The eyes are actually curved, not flat. So maybe I misunderstood your flat here.
Yes, you are right. For the insect, they normally have the general curvature of their eyes. And for each eyes, it's also not flat, it's curvature. But for their eyes, for example, for the fruit fly shown here, normally they only detect 3 wavelengths. One for their food, they eat the sweet, okay? So they detect the sugar, okay? One for their enemy. They actually want to see their enemy. They want to escape. One for their mate, their wife or husband. So they only work for 3 wavelengths for their eyes. And also they had a very wide angle. But for our cases, because our each lens is flat, but in the future, we want to learn from them to make this flexible eyes on the sphere. So, but each of the lens is flat. It's good. And each of lens is broadband because we want to see clearly. We not only worry about our enemy, we not only like our mating process and our food, and we also have the social activity. So we need a broadband wavelengths. So that's why we want to learn the good things from them, and we want to keep the advantage of our lens. Yeah.
Thank you very much.
Yes.
Thank you, Professor Chai. Now, Professor Kim, look, you can unmute and please speak.
Hello, Tsai, very nice talk. I have some question actually. Regarding your antenna design, I think it's just to adjust mainly adjust the dimension to adjust the phase. Is it possible, for example, to also to adjust the magnitude, the reflection of the magnitude in order to achieve some other special performance? This is the first question I want to ask.
Yes. Very good question. I will answer you. See here, this is the narrow antenna. Okay. Basically, we want to cover the not only the very high efficiency and also the phase coverage, okay, from 0 to 2 pi, okay. So you can have the amplitude control, and also you can have phase control by change your narrow antenna shape or geometry size. Okay, but this case is very original because they have the different size and the total interaction cross section. For different narrow antenna, they are different amplitude. So this is a disadvantage for this type of system. And so that's why people use PP phase. PP phase means the narrow antenna shape and the size is the same. But by rotating the narrow antenna direction, then you can find out the phase will change according to the rotation angle. It's 2 times. So it's very phase control. So, but still, the advantage of this is the amplitude of each of these interaction cross section are the same. Mm-hmm. Okay, because they are the same interaction cross section on the total surface area. Mm-hmm. But still, even in this case, you think about it, the coverage of the narrow antenna is always limited compared to the total surface area. Mm-hmm. So you won't be able to have 100% efficiency. Mm-hmm. Otherwise, it will be a thin film. Mm-hmm. So no narrow antenna. So that's why people try to improve this case, and that's why I mentioned about in order to have all this optimization of your incident light and output EM wave, you have to consider what you want, what you need, and what's the limitation of your narrow fabrication process, and also the total meta device size. Because if you want to have very efficiency, or you have different function, you want to make it large or you want to make it small, it's all different. So that's why until today, because we think too much, therefore we worry about too much. But if we think very straightforward for single wavelengths or for one purpose, it can be very easy to do it for single purpose devices. Yeah.
Okay, thank you. A second question is, have you tried to use different kinds of metals in order to check which one has better performance?
Yes, you are right. I actually choose these 2 cases. One is gold. Okay, so in this case, the coverage is from the wavelength coverage is for infrared. Okay, from the 1200 to 1680 nanometer. Mm-hmm. And for the aluminum, another case I show you for aluminum, in this case, the coverage is for 400 nanometer to 670 nanometer. It's invisible spectrum. Mm-hmm. So the material you pick or you choose is very important. And So you can also mix up the different material. If you have a photo mask or EB mask, multiple mask, you can actually deposit different material to make the chosen bandwidth or the working wavelengths shift according to what you want. Yeah. So for the metal and for the dielectric, the third one I show you is gallium nitride. It's semiconductor, more like a dielectric material. So they are all different. So you can choose different for different purpose and application. Yeah.
Actually,
we try titanium oxide or titanium nitride or different material. Yeah.
Actually, what's the percentage of energy going inside the metal, or the major portion of the energy is bouncing back and forth between the aluminum, the two aluminum layer?
Yes, you are right. For example, in this case, aluminum is very easy to be oxidized. So the efficiency of this kind of nano antenna compared to the gold basically had a higher efficiency than this one. So it's 31%. So because the gold will not be oxidized easily in this case. So it all depends on the material and also the design. Yeah, and we also choose the silicon oxide as a dielectric layer to control the coupling between the nano antenna on the top and underneath the mirror image. Yeah.
Okay. So I will ask you more questions later. Yeah.
No problem. You are very welcome.
Yeah. Okay. Thank you, Professor Tsai. Yeah.
Thank you. Thank you. Now the next question from Ho Xiao Lu. Please, could you turn on the camera and ask the question?
Yeah. Can you hear me, Professor Tsai?
Yes.
Thanks for your very exciting talking. So I want to ask a question. As we can see, the achromatic maintenance has a relatively low numerical aperture. Is there any way to achieve both achromatic performance, broadband achromatic performance, and a large numerical aperture?
Okay, good. This is a very good question. Like I mentioned previously, depends on what you want. Okay, you can always go to what you need. If you want to make a large numeric aperture, and of course you can make a large numeric aperture. You can design, you choose the right material and the working wavelengths, but it will never be perfect for you. The reason is very simple. Many constraints for fabrication, for material property, for different reasons. So you still have to compromise or optimize your system based on this. So I think no problem. There's no problem for you to choose the large numeric aperture, and I don't see any problem. You can just do it as you wish, but you have to choose the right material, and you have to design the good nanostructure, which is easily for you to make.
Okay, thank you very much.
Thank you. Thank you. The next question is from Professor Stella Payne. Could you unmute and turn on the camera?
Thank you, Professor Hong Yan. Professor Tsai, you have given a very wonderful talk. It's very enjoyable. Thank you very much. I just wonder, you mentioned that there are now all the elements that is ready to be made into different applications, right? By modulating the waves. Why is it now currently that none of these matter devices and surfaces how come they're not already applied in various products? What is preventing it from being put into real products or applications right now?
Yeah, okay. This is a very good question. that's why so many different universities want to have my student. Okay, and I think it's matter of time. Many of my students in Switzerland, in Lausanne, and also in Caltech, Harvard University, in different areas in Japan, they are doing this meta device fabrication and design for different purpose. And I don't see the problem, but if you ask me the problem, I don't have e-beam lithography in EE. If you have an e-beam lithography system for me in EE, I can make a lot of samples for you. Yeah, we can design and fabricate a lot of samples for you. So I think the facility in the EE it should be after we learn how to make the sample, we can make a lot of samples for different applications. Yes.
So I mean, not just in our university department, but actually in terms of making it commercial, right? Actually commercially available for others to produce it and make it in production. What is holding it back?
Okay. Yeah, most of the people, they still learning this new method, and that's why I introduced this novel method to use differential phase equation and the edge alignment and the integrated resonance unit. Those three are important concepts for you to have a general design rule, and also to design the mask, and also. But for the mass production process, I see most of this semiconductor company, they can make it easily, because I believe now it's 5 nanometer or 3 nanometer technology available for our system. It's 10 or 20 nanometer system, so it's readily available for us to make this kind of system or meta devices for commercial use. That's why in the beginning of my talk, I asked this question. I show you basically the meta device drone already in the sky of the CityU. So, and I don't see any problem. Just I don't want to make the competition with the traditional optics, because this optics is readily available and it's inexpensive, and you don't need to replace this kind of system without much of this effort. So I think we should do this novel function. We should think about the new function of our meta devices, and also especially in the metaverse, we can make tremendous support and help for the implementation of the metaverse. Yeah.
Thank you, Professor Tsai. Yeah.
Yes. Thank you. Thank you for your comment. Yeah. Thank you.
We also have 2 questions on the chat. Let me read them. The first question is, what are the limitations of meta surfaces?
Okay. The limitation is always there, like I mentioned here. Okay, if you want to make something come out for you, you have to choose the right material, and you have to come out this very optimization of the function, the requirement from your function. So you can using this general principle design rule to achieve what you want. So the limitation, for example, comes from the fabrication, the critical dimension of your fabrication system, so-called, like I mentioned, now the semiconductor electronics company in Korea and in Taiwan, they claim the 3 nanometer or 5 nanometer critical dimension, and also this is a limitation. And also, you always has to choose the right material for the permeability and the permittivity shown here is in order to have this A and K available for you for your working wavelengths or your bandwidth. Yeah. So this is the limitation. The limitation is physics. Yeah.
Thank you, thank you. We have another question on the chat. The second question is, what is the bottleneck of meta surface for wide applications, such as fabrication or design?
Okay, yeah. Like in my talk, I don't see the bottleneck. The bottleneck is, I think you need a good environment to implement all your design and the fabrication. That's the current bottleneck. And also the pandemic, we cannot travel. We cannot communicate with people. And I think that's the bottleneck. And other than that, all the limitations come from physics. Not too much to say about it. Yeah.
Thank you, Professor Tsai. Any other questions? If not, I'd like to thank Professor Tsai for the very interesting talk, very inspiring talk today. And sorry, we have one more question. One more question just came on the chat. What roles of mathematical, of meta material plays for quantum optics?
This is excellent question. Okay. I think this picture will show you the future of the high-dimensional quantum optic chip is very important. The reason is they can have this correlated and entanglement states within one single chip at room temperature, not this liquid nitrogen or liquid helium temperature. Okay, and it can be portable, wearable, or even implantable to your body. So I think this kind of system will have a huge impact very quickly, and this is people expected for this direction, and the good prospect in this direction. Yeah.
Thank you, Professor Tsai. Any other questions? If not, let's thank Professor Tsai for the wonderful lecture. Thank you very much.
Thank you.
And in the series, we have two more talks on electronics and photonics. One will be given by Professor Michael J. on 12th of April, and another one given by Professor Chi Chen on 22nd of April. You'll be welcome to attend those lectures. So I would like also to thank all the attendees for coming to this lecture. Thank you very much.